Yeah, so Tim, hi, we are already live and welcome Tim again to our fourth session. That's the last session by Tim. And this is just to tell students that on the website, all the material he shared with us has been put in the homework and quizzes section. That's it. So, hi, we are already live. And welcome Tim again. Sorry, oh God. Our fourth session. That's the last session by Tim. Okay. And so we have requested students to have a look at the material that's there on the website and and then get back to us. Sorry for that disturbance. So Tim, over on to you, and we can start.
Okay, well, good morning, everybody. Um, so glad to see you all back with us today, this morning. Um, Today, we're going to go over gravitational lensing, and we're going to use gravitational lensing. Well, one, we get to see the pictures, which is always nice, but we're going to use the effect of gravitational lensing in order to measure the amount of dark matter in galaxies. So, first thing to do for us is to go and get data here. And I just realized, okay, I need to close up that there. Okay, I'm going to go to the, we're going to go to the Space Telescope Science Institute's online archive. Let's see here, let me make sure I'm sharing my screen so that y'all can follow this. Okay, share screen. Step one and share. Okay, now can everybody see the web browser that I have here? All right, oh, and let me get the chat window back open too so I see that. Okay, good, thank you. All right, so now let's see, to tell you the truth, I'm slipping up a little bit and forgetting whether I have shown y'all the Space Telescope archive or not, because of my own introductory astronomy class has been doing some of the same material here. But anyway, we're going to go to archive.stsci.edu, and I've put the link directly into the chat window. So we're going to go and download one gravitational lens image to start off with, and then you can follow along with the same work that I'm doing. All right, so let's go scroll down here to access MAST data. If you remember from the previous time we were here, MAST stands for the Mikulski Archive for Space Telescopes. All right, so we're going to go to the portal. The portal is a fairly modern style interface for it. They've been working on this for a few years and brought it out live. Oh, it may have been 5 years ago now. Service interruption notice. Uh-oh, let's see here. Saturday, October 3rd. Okay. Nope, that's good. We should be fine right now. That should be back up. All right, so we're going to do a search here, and let's see. What I want to do is go to advanced search. And so you click that over. It's on the right-hand side there of the search window, search field. Okay, it brings up this floating window on top of this. And what I want to do is to put in the proposal identification. Okay, so there was a proposal when astronomers want to use the Hubble Space Telescope or any telescope, you write a proposal, which is, oh, it may be about 5 pages or so. And you write out you make the case, the argument for why the science you want to do with it is worthwhile, and you explain what the scientific value is going to be, and you describe what you're going to do with the data. And then, of course, you put in what objects you want to look at and the exposure times and things like this. So when you submit this, your proposal is given an ID number, and I have written down the ID number for the proposal we're going to look at. Okay, I'm copying this, and if I can find, oh, here we go, and the cat just got up in my lap. You may be seeing a tail stick up every now and then. Okay, and what I want to do, here we go. Scroll down to proposal ID, and you're going to put in this number here, 10494. This must be searched via the text. Okay. So I've entered that, and we just hit enter or return after we do that. Once you've got that in, you should see the applied filter, proposal ID 10494, and hit search. And there's a list of galaxies that were observed with this proposal. All right. So we've got here a list of all the various images that were taken with this. And what we want to do, let's see, I want to find the right one. So if we scroll over, you can scroll left and right in this display here, and the target name, and it's given name Galaxy, something or another like that. And so the one we're looking for is this one. I'm putting it into the chat window. Okay, so let's go down to that one there, 0668. And it's in numerical or alphabetical order. 0668. It looks like it skipped. Here we go. Here we go. All right, and you'll see that there are, 3 images that have that there. The difference between these is the first one on the list here was taken with a different filter than this one here. So we have 2 different filters, and then I'm not sure what that refers to, but we don't need to bother with it. Okay. The filters that the Hubble Space Telescope uses have a name that is given with F is the first letter, which just stands for filter. Then the next bit are numbers. That gives us the wavelength of the filter, the central wavelength. In this case, it's in nanometers. So 555 nanometers, which is yellow to green, that part of the wave band. And then we have a letter afterwards. If it says W, that means a wide band filter. Those are the normal filters we use. You also can get an M for medium band filter, so that covers a narrower range of wavelengths. And finally, an N for narrow, which would be a specific wavelength there, or specific emission or absorption line. All right, so we're going to download both the 555 and the 814 filters. We're really going to do the science on the 814 filter, but the 555 would be a nice thing for you to download because you can make a color image out of this, and it's nice to see what those look like. So if we scroll all the way back to the left, okay, this is a little tricky to get here. I'm going to select images 64 and 65. Now those are highlighted. Okay, and I'll just make sure that I've got the same things there that I had expected. We see the file name, HST for Hubble Space Telescope. 10494, that is the proposal number. 09, not sure about what that is. Oh, maybe it's just the target in a list in order. ACS means the Advanced Camera for Surveys, which is the camera they used. WFC is the wide field camera setting within the advanced camera for surveys. And then finally, the filter name. So that's what all of this means. And then we have the right ascension and declination, the date in which it was taken, exposure times, and so on. All right, so we have those two selected, and we're going to go up to this icon, if you see my cursor here, and that is the add it to your shopping basket. I've clicked that. Okay, and now we can go straight to, let's see here, we need to select both of those with the little selection boxes. And we see now the download option has appeared over on the upper right-hand side. So hit download selected items. Okay, zip them. Oh, pop-up blocked. I've got to go to my options here. Hang on, and that may be a problem for some of you too, if you have pop-up windows blocked. Okay, let's see here. Privacy and security, I think it's where that is. Well, that's where I thought it was. Security, site settings, here we go. Okay, pop-ups allowed. There we go. Now let me try. There we are. Okay, so we'll put these here. I put it into a folder just for this morning's lecture. Okay. Now I'm going to go over to the location, show in the Finder here. Okay, so let's take a look at what how the image appears. All right. So I've here opened up the image within the DS9 program, the FITS image viewer. And I'm taking a look at the 814W filter. Now, 814, that is 814 nanometers, and that corresponds to the near infrared. If you're familiar with the standard Johnson filter set, this is the I band, or which again stands for near infrared. 814 wide is actually closer to the cousin's I. You'll sometimes see it written as I and with a C for a subscript C standing for cousins. And the cousins version of the infrared filter is a little bit different from the standard Johnson filter, but they're very close to each other. Okay, mine have downloaded. I'll show you how to open these and which of the files you're going to want. So I am unzipping it. Okay. Now we get this folder here. I'm going to trash, if I can. Here we go. There we go. Trash the original file. All right. We've got two subfolders in here. And let's see here. So we've got it, HLA is the Hubble Legacy Archive. And for this, they've generally got it that's the version that we want. If you look in the folder labeled HST, Hubble Space Telescope, we get different code letters on this, and this is specific to the camera and the setting and so on like that, and which observation is taken with that camera and setting, with starting with 1 from the beginning. So if you get this here, this is probably, let's see, that you should be able to do science with that one there. That DRZ stands for drizzled, which is a combined set of several different observations, several different exposures put into a single file. But I know that the HLA, the Hubble Legacy Archive, they've gone through and done more calibration and processing and so on. And so I'm going to do it from this here. Now, I believe, okay. When I saved it, I did this a few years ago, and my file comes up with a different name on it, and that's probably just how I had named it then. All right, so you should see, if you open it up, you should see something like this. I'd better confirm that actually does look like it. Ah, okay. You're going to see it tilted, and that's because they have oriented it with the north direction up. So let's go to the version that you have here. I'm going to delete that, and this is what you should be working with. Make that a little bit bigger. So first step is to find the target. Now, if you take a look at this, this is a wide field camera. There are a lot of things in this picture. So if we're not sure what the target is, we can go to the header. If you're using DS9, you just go to File and Display Header, and any FITS image viewer should give you the ability to display the header. Now there are 2 headers for this one here. There's the science header, and then there's a general header. I'm not sure which one it's going to be in, so let's go to the general one first. Okay, and what I'm looking for is the right ascension and the declination of the target. And so it won't be that far down. So I think it's going to be in the science header. Okay, so I go to display header. I choose the second one. Okay, here we go. Aperture reference position, that's a little bit different. Yeah, to tell you the truth, I thought that it was going to be located in there, but it's just going to tell us the center of it. Well, in this case, I'm going to rely on being able to see it. So I'm going to adjust the brightness levels. I think it's this big blob here, but I need to make the upper level brightness a little higher. Okay, so I brought the upper level brightness up a bit. And let's zoom in and take a look around. So I'm adjusting brightness and contrast. It's a spectacular pair of galaxies, but I don't see a lens there. What we're going to be looking for is a ring surrounding the galaxy. Let's see if it's maybe in that one. Nope. Maybe this here. There it is. Okay, it's a smaller one. So let me show you where it is in the field of view. You should see something like this, and you go over to the right-hand half of the image, and it's right in the center of that. Okay, right there. All right, so what we're looking at is a galaxy here. This is probably an elliptical galaxy, and then we see this ring caused by a distant galaxy behind it that is almost perfectly lined up. Now, let me give you a little background on this. I've jumped right into the image so that we're ready to go, but you need to see how all of this works. I believe that Priya has posted the PDF of tonight's chapter on Telegram, and so you can get that there. Let me scroll to the beginning of this PDF. So this is my chapter 21, Measuring Dark Matter from Gravitational Lensing. I don't know how familiar all of you are with extragalactic astronomy. If you've been doing mostly stellar work, you've been looking at things in the Milky Way. But now we have to start accounting for cosmological effects. Take a look at the diagram at the top of this page, page 122. It's the second page of the PDF file. And I'm going to zoom in on it. Okay, so if we're here on the Earth, on the right-hand side, and let's say we have a distant object, which we'll refer to as the source, meaning just the source of light. It could be a quasar, in many cases it will be, or it may be a galaxy. The light rays coming from that object, that distant object, will spread out all through space, going off in all directions evenly. One light ray would normally come straight to us, but now let's put a galaxy or a cluster of galaxies in between the Earth and our distant source. In that case, the gravitational pull of the galaxy in the middle will act as a lens and will bend the path of light. This path normally would not have hit us at all. It would have gone up and to the right and would have missed the Earth. But the gravitational pull of this galaxy in a cluster bends it over and aims it directly at the Earth. At the same time, a light ray that would have gone down below the Earth and missed us down here is bent upward at just the right angle. And you might say, well, what are the odds of it being bent at just the right angle? Well, we're only going to see it if it is bent at just the right angle. So we do not see lensing everywhere. In fact, it's a very rare phenomenon. This is what we call strong gravitational lensing, but it does happen. Strong gravitational lensing is what I'm showing in the diagram, and it is where you will see strongly distorted views of your distant source, or you'll see multiple images of it, and that's what's happening here. Because this light ray is going up and to the right, and then it's bent down to the Earth. Our eyes assume that light rays travel in straight lines. And so our eyes tells us, well, the light ray came from this direction. So we mentally trace this back and we say, all right, there's the object, it's up here. But at the same time, this lower light ray would have gone down, but it bends back upwards towards the Earth. And so our eyes trace that light ray back and we say, there is a second source down here, which just happens to look exactly the same as the first. So we get multiple images this way. Of course, we could also have a light ray that would come out of the page, is bent back into the page by the galaxy and hits the Earth, and we'd say there's one to the left. One that goes into the page would come out, we'd say it's to the right. And if it were perfectly lined up, there would be an infinite number of these light rays at all different angles in a cone, in all different directions, arranged in a cone that would all be focused on the Earth, and we would see that distant source stretched out into a ring. And that's what we'll work with tonight, this morning. Okay, so I've given the background of gravitational lensing in the first section here. Examples of strong lensing that you'll come across frequently. On the top of the third page, page 123 in the text, this top image here shows some of the early pictures gravitational lenses taken by Kavan Ratnatunga, who was uh, at Carnegie Mellon University back at the time. And these were some of the earliest ones taken with the Hubble. What you see in red or orange is the lensing galaxy. Now the lens is the galaxy close to us. Okay, here on the left, and a second one on the right. Now it's colored yellow to orange to red because it is an elliptical galaxy, and that's typical. Elliptical galaxies tend to be the most massive ones we have, and therefore they have the strongest gravitational pulls and create the strongest lensing. The blue dots around it is the light from a distant quasar, so that's the source. The quasar appears blue because it has a very high temperature thermal emission from an accretion disk orbiting a black hole. And that hot temperature drives the light to be very blue. Okay, now the quasar is it's a very tiny source of light. You're seeing a region of emission that is, it could be less than a light year across even, and at a distance of many billions of light years away. So it will appear simply as a dot. You don't tend to resolve the light of a quasar in most cases. And so what we see in this case is we have a symmetry. You see this dot on the upper part here and the lower dot, and then the one to the right and the one to the left. You see a better image of this on the right-hand side. All right. The splitting of the images occurs along the lines of symmetry of the lens. So in this case, the case on the right is an easy case to make out. We can resolve the lens as an elliptical galaxy. Now it has a long dimension. The long dimension runs from the upper left to the lower right, this way here. And so we get one line of symmetry there. Along that line of symmetry, we split the image of the source into one on the upper left side and one on the lower right. Then we have the short axis, the minor axis of the galaxy, of the elliptical galaxy. In that case, that makes another line of symmetry, and so we have one image of the source to the upper right. Together on that direction. Oops, sorry, my internet connection is unstable. If anyone has trouble hearing or seeing me, just make sure and tell me in the chat window.
Yeah, so sorry, Tim, just a minute ago, you did, your audio just went.
Okay.
Repeat the last.
Was there much that was missing?
No, just maybe a minute, not more.
Okay. So we will have a greater splitting of the images along any line of symmetry of the lens in which the mass is compressed into a shorter distance. Now, down here, I should say that whenever we see four images of the source, that is called an Einstein cross. Forms a cross image, and it's named for Albert Einstein, of course, who had predicted the possibility of gravitational lensing, although he thought it was unlikely we would ever see any because the angles involved would be so small. Well, our telescopes just got bigger and bigger, and we could see finer and finer details. Okay, now if we have a spherically symmetrical lens and our source is lined up very perfectly behind the lens, then it's possible to get the images of the source smeared into a ring or close to a ring, and that's called an Einstein ring. If you take a look in the lower images here, we get several, let's see, this one in the second from the left on the lower row, that is pretty much a perfect Einstein ring right there. On the bottom right, That's also, I believe, a perfect Einstein ring, and we get just about a complete ring on the upper left. And in most of those cases, again, you see that the lens is almost a circle and would be spherical, would appear spherical from this direction. The more elongated and elliptical the lens appears, the less likely it is for you to get a perfect circle, a perfect Einstein ring. But it is possible, and it depends again on the distribution of mass within the lens. Okay. Oh, now in this case, I should note, once again, this is a much more recent image. The first one here was taken in 1995 with the old Wide Field Planetary Camera 2, WIFPIC 2 there. That was the original main camera installed on the Hubble when it was launched in 1990. But more recently, we've got these other cameras that have been put on, and let's see here. This is the Advanced Camera for Surveys, and PRC press release something 05, so that's 2005 that these were taken here. Okay. So I was going to mention the colors. The colors look a little bit different because the filters used were different as well. But you still have a more or less red galaxy. Now, again, to an astronomer, there are two colors, blue and red. So, and we kind of exaggerate. I would consider this to be yellow, say, maybe a little bit orange, but we'll call that red. Again, because it's an elliptical galaxy that usually does the lensing and therefore has an older stellar population. So those blue giant stars have evolved off the main sequence and are now red giants. And the ones left on the main sequence are also red, the smaller, redder stars, so the whole galaxy appears red. On the other hand, the lensed source appears blue again. Now, you might think, well, look, if you know about the expansion of the universe, the farther away something is, the higher its redshift, and therefore the redder it should appear. But our distant source appears bluer. That's because the color is not coming from the redshift, which is actually still moderate in these cases. And so it doesn't really change the visible color enough to where we could tell with our eyes. But instead, it's far enough away that it's coming from the earlier universe, and where you have a larger population of spiral galaxies that are forming stars. And that ongoing active star formation causes these to look blue. So it's active star formation, blue, versus no star formation, red. Okay.
Tim, I'm sorry to
Yes.
interrupt, but I think the net is creating a problem. So maybe you should switch off your camera. Though we'd obviously like seeing you, but
Switch off the camera. Okay.
yeah, maybe that just gives it better bandwidth.
Yeah.
It's a loss not to see you, but I think that would maybe solve the problem because the
Okay.
audio is going off on and off. Yeah,
Uh-huh.
sorry.
All right. Hopefully that will take a little bit less then. All right, and I'll speak a little bit slowly so that if there's a small glitch, it might not remove too much of what I'm saying. Okay, I've given a link here to where you can try out a demonstration of the effect, and it's actually worth taking a look. So we don't need the MAST portal anymore. Now, this page was put together, oh boy, about 20 years ago, but it's still up, thank goodness. So this is a simulation of what gravitational lensing looks like, the effect of it. If you take a look here at, let's see, these bars, the buttons underneath the image, show you, if you start off with the original image here on the left, we click that one. Now let's move a lensing, a lens closer into the image. So here, he has, the guy who created this had created some distribution of mass in here, which is cut out in white. That's exaggerating the size. It's just, I'm not entirely sure what that pattern shows you. But this ring here shows you where the Einstein ring will be for any source which is directly behind the center of the lens. Let's take a look at the effect on this galaxy here. Okay, that'll be our source. As we bring the lens closer to the right, by pressing the buttons farther and farther to the right here, notice that we get two images of the source. One is outside the ring, and it's where the normal location would be, but slightly distorted by the presence of the lens. The second one is inside the lens, inside the radius of that Einstein ring that we'll eventually get. So you see that one here. Keep an eye on that. That's going to be growing. As we bring it closer in, you see that the smaller image to the left here is growing, and it is moving outwards towards the Einstein ring radius. While the image that is outside the ring is more distorted, is being pushed a bit to the right. It looks like it's repelled by the lens, and it's being distorted into an arc. As we get closer still, we see that the inner image is also distorted into an arc. And when we get it to where the lens position is lined up with the source position, the two of them merge into the Einstein ring. If we continue on to the right, we see it repeating the pattern in reverse. Okay, so if they're right there, that's the perfect Einstein ring. But what you'll typically see is something very much like this, where you see that inner distorted image and the outer distorted image. Okay. All right. So I've given you here in section 21.1.1 a derivation of the total mass of a lens. If we know the distance to the lens and we know the distance to the source. Now, first, there's actually a very simple version of this. I'm going to use this cursive letter M to represent mass because we often use the Roman form to represent the magnitude. So that way I distinguish. D is going to be distance, and we'll measure the distance in megaparsecs, millions of parsecs, right there. Now we're going to, because typical distances may be on the order of about 3,000 megaparsecs, I'm going to divide the distance by 3,000 megaparsecs, and typical masses will be on the order of 1 trillion solar masses. I should be careful here. I know the American dialect and British dialect is different for millions and for billions and trillions. And so I don't know what the Indian dialect of English uses. So I'll just say 10 to the 12th power is a typical value. Now, the radius, the angular radius of the Einstein ring will represent by theta sub e for Einstein ring. And then we'll scale that by 2 arc seconds. So we take mass to the 1/2 power times distance to the -1/2 power, appropriately scaled, and multiply that by 2 arc seconds. This gives you a very rough, approximate value for the radius of an Einstein ring. If you turn that around and solve for mass, you'll see that it will be 10 to the 12th power solar masses, angle divided by 2 arc seconds squared, all times distance over 3,000 megaparsecs. Okay, so this way we have everything scaled appropriately, and we find that if the distance to the lens were 3,000 megaparsecs, and we had an Einstein ring with a radius of 2 arc seconds, we would find the mass to be 10 to the 12th solar masses. And these, again, are fairly typical numbers, but the true value depends really on the distance to the lens and on the distance to the source itself. So if we want to do it right, we need to measure both of those. So here's the correct form of this equation, equation 21.1. Now, I've got, we need to use subscripts to keep track of this. Again, theta e is the angular radius of the Einstein ring in arc seconds. Script m is the mass of the lens itself. We don't know the mass of the source, and we don't really care in this case. G is the gravitational constant. C is the speed of light. Now we have three distances that are involved. I'll start on the bottom. Let's use S to represent the source. That's the object which is producing the light, and that's the very distant one. Like I said, usually a quasar or a blue star-forming spiral galaxy. O will represent the observer, that's us. So D sub SO is the distance from the source to the observer. D sub LO is the distance from the lens to the observer. That's going to be, the lens is the closer one, usually the red elliptical galaxy. And then we've got the distance from the source to the lens. That's a little bit trickier. Now you'd say, well, look, we can get the distance from the source to the observer.
We've lost your audio again.
Oh, sorry.
So you'll have to repeat the last sentence. Sorry.
Okay. So I'll scroll here to the mass, where I've simply solved that equation for the mass. So how do we get the distance from the source to the lens? Well, you might think, well, if we know the distance from the lens to us and from the source to us, then we just subtract one from the other and we have the distance from the source to the lens. However, this is cosmology and it's never quite that simple. So we are going to be using distances. Good, I did draw the diagram here. We're using distances that are called angular diameter distances. Okay, which it's the ratio of the galaxy's physical diameter to its angular diameter. So if we have something close by, if we're looking at a mountain a few miles away, and we take the height of the mountain and we take the angular size of the mountain, and we divide them, that would get us an angular diameter distance. That's going to be pure geometry, normal, plane, Euclidean geometry. However, when we're dealing with an expanding universe and objects far away in that expanding universe, it doesn't come out to be the same. It's not Euclidean space then. We have a curved space that we're dealing with. Okay. If we have something very close by, then that even nearby galaxies, simply dividing the physical diameter by the angular diameter gets us what we would expect. That would be the same thing as the physical distance. But if we get to a redshift of about, if you all know redshift Z, Z is defined as the recession velocity divided by the speed of light. And because the universe is expanding, the farther away something is, the faster away it is moving. And that's that faster way it's moving, that's the recession velocity. So divide that by the speed of light. We get things that are at a redshift of about 1, which means that the stretching of space is moving at about the speed of light relative to us. And we can get things that are redshifts much greater than 1, by the way. That doesn't violate, it's not that the physical object is moving faster than the speed of light, it's simply the distortion of space doing this. Now, once we get past a redshift of 1 and to greater distances, the galaxies don't look smaller, they look larger the farther away they get. Basically, the curvature of space, or the expansion of space, is magnifying them in that way. So things don't behave the way you expect with that. And that means that the distance from the source to the lens plus the distance from the lens to the observer is not the same as the distance from the source to the observer, despite the way I made it look when I drew the diagram up here. So in order to do this, in order to find those distances, we need to, there's some calculus involved, but we can calculate this using Ned Wright, who is a cosmologist, and his handy online calculator there. So we're going to need to find what's called the angular size distance and something else called the co-moving radial distance of that galaxy. And we'll use the Greek letter chi to represent a co-moving radial distance. Now, I apologize, I'm having to throw in a bit of cosmology here, which may be new to some of you, but we'll get to the images soon enough here. If we need to find the distance from the source to the lens, we use those co-moving radial distances. Now, what are co-moving coordinates? If we were to draw, let's take a helium balloon, and we're going to draw a coordinate system on the balloon, and then we blow up the balloon. I guess it's not a helium balloon, it's an air balloon. Well, it's a balloon, and we blow it up and it stretches. Co-moving coordinates stretch as the universe expands. So those would be the grid lines that we draw on that balloon. And so if a galaxy is not moving, now this sounds like I'm violating the rules about relativity itself, right? If the galaxy is not moving through space, but simply it's space itself that is expanding, and that's why the galaxy gets farther away, its co-moving distance doesn't change because of that. This gives us a coordinate system that scales with the size of the universe over time. All right, so we'll look up the co-moving radial distance of the source, that's chi sub s, the co-moving radial distance of the lens, that's chi sub l, and we need the redshift z of the source too. And here's a simple equation that gets you the distance from the source to the lens. Okay. Then measuring the radius, angular radius of the ring is easy enough, and we're going to go to our FITS image viewer and get it that way. Okay, I think at this point we should go straight on into the image, and we'll do the math last. So the first thing we want to do is, well, we want to open up the image. We have found where our lens is, and we want to measure the radius, the angular radius of that of the ring, of the Einstein ring here. Now, the one I chose to start with, unfortunately, is not really the best example for that, because it's not nearly a complete ring. But I don't want to spend the time to go and download the next one while we're all here together. You can do that later on. So what we'll do is we're going to create a region in DS9. Now, if you're skilled with using the FITS image viewer, you've probably used the regions option before. If not, you have all these. A region is just it's a shape that's drawn on the image. I have it set up to where when I click on it, and probably if you're using a Windows machine, you would be using a left click, but I think that can be changed. You by default, you get a circular region. Now we can expand the region by putting the cursor over one of these tabs. There are 4 tabs on it, and make it larger or smaller. Okay, we can shrink it in like that. The first thing I want to do is to center the region on the galaxy, on the lensing galaxy. You see here, I think that that's a little bit off. I think it could be centered better. So what we can do is we go to region. This is the region menu, and we scroll down to the centroid option, and you see it shifted it a bit. Centroid is a useful tool, and what it will do is to center the region on the light that is within it. So if you have a bright source of light, it'll get it so that it does a weighted average of the position of that light source, and it will center it on the weighted average. Okay. Now, from there, we expand the region until we are cutting the ring with the region, with the circular region. So it looks like we've got the ring right on that line. I'm going to make it just a little bit smaller, about like that. Now, in some of these cases, you'll find that the Einstein ring is not perfect around there. It might be a little elliptical. And I'll show you another example of that later on so you can tell what to do when you get to that case. Okay, now we're going to use this to measure the angular radius of the ring. So I am double clicking on the region, or if it doesn't work for you, if your mouse is set differently, DS9 has a lot of customization you can do, but it also means that it can be a little frustrating to get it to do the same thing as what someone else's does. You go to the region menu and you go to get information. Okay, it tells me this is a circle shape region, which is, I knew that. It tells me by default, the right ascension and the declination of the center, and then the radius, which is what I really want. Now you have different options here. WCS stands for World Coordinate System, and that means it's going to use information in the header of the FITS image to translate how many pixels means how many arc seconds across and so on. And you can have many different world coordinate systems for the image. I've never known why you'd want more than one. We're not going to use that. You could also select image or physical or amplifier detector. Mostly those give the same results, which would be how many pixels across. Okay, but we want the world coordinate. 0.50 arc seconds. Okay, it looks like my internet gave a little glitch again, so I'll repeat that. We're going to write this number down, that theta sub E is 1.50 arc seconds. All right, that's that first part of information we need. I'm going to move this out of the way so you can see what we're doing here. All right. Now, the next thing we're going to do, well, let's see here. We need, let's go on and get the mass. So we need to look up the distance to this source and to the lens. And to do that, we go to the NASA Extragalactic Database. Let me bring this back here. And that will allow us to get the total mass. All right, let me see that I've got a link for you. Well, we need to know what the source is first. Okay. In this case, well, I've got a table here, and here we go. A table of gravitational lenses that we're using here, and I have looked up what the lens and the source redshifts are. That's the kind of thing that in practice you need to go to a database that has these listed in them, or you go to the paper where this was published. In this case, I believe I took it from the research paper, and I'll give a link to that paper later. I'll send that on to Priya so she can post it so you can find it. The NASA Extragalactic Database could be used for it, but you got to be very careful and know what the source and what the lens are on that there. Okay, well, let's find out which one are we using here. The short names for each of these are usually coordinates, right ascension first and declination second. So we see 0216, that's right ascension, 2 hours, 16 minutes, minus 0813, negative 8 degrees, 13 minutes. So let's figure out which one this is here. If I go back to this, perfect, that's the first one. Okay, you see here, our right ascension and declination match that of the first one on the list. And so we know that the redshift of the lens, that Z sub L, is 0.332, so write that down. And the redshift of the source, it's higher, 0.523. All right, now we'll go to Ned Wright's Cosmology calculator. I'm going to go back up a few pages and I'll give you the link in the chat window. Okay. I'm going to move this out of the way again. Now, on the left-hand side of this here, he's got the cosmology that you assume for the universe. He has default values, which you should leave as they are, unless you are a cosmologist or somebody working with a team that has different assumptions about it because you've done the research on this. So the value for H naught, that is the Hubble constant. That is the expansion rate of the universe today. 69.6 is a broadly agreed on good value for it, although there's starting to be a bit of debate again. Omega sub m is the density, the relative density of matter within the universe. And then omega sub vacuum, VAC for vacuum, that's the relative density of the vacuum energy, which is a popular explanation for the so-called dark energy, which is causing the accelerated expansion of the universe. So it's making up 71.4% of the energy of the universe. Okay. And then we have whatever redshift we want to put in, that Z is what we're going to change. So in the place for Z, let's type in the redshift of the lens, 0.332. Now, you have three buttons, open or flat or general. Open and flat impose a geometry on the cosmology of the universe. An open universe would have a hyperbolic geometry, negative curvature, and flat would be a zero curvature to the universe as a whole. And in fact, we are pretty darn close to flat. But let's leave it as general because the numbers, the default numbers in here for omega matter and omega vacuum give us the correct value. So we're going to hit general. Okay. And the page on the window, what do you call it, frame on the right has now updated. Okay. Here are the values that we entered. And you see that our redshift is up there now. So make sure you've got the correct redshift in there. Otherwise, the page may not have updated. And tells you a little bit about the universe at that location. Okay. Let's see here. What we want is we want the angular size distance. Now, there are different terms. There's the angular diameter distance and the angular size distance. Both of those mean the same thing. So we're taking d sub a, distance angular, and we're going to write it down with the units, 993. So that's, let's see, this is distance from the lens to the observer, d sub LO, is 993.1 megaparsecs. Okay, we're also going to write down the co-moving radial distance. Okay, and that is chi, Greek letter chi, subscript L for lens, and that's equal to 1,322.9 megaparsecs. Okay, now let's put the redshift of our of our source, the Z sub S. That's at 0.523. And I hit general for the button again. Okay, that I saw it blink, so it's updated, and sure enough, I have the new redshift up here. Let's take a look at the angular size distance first. So the angular size distance is what we wrote down as d sub S O, distance from the source to the observer. That is 1,303.1 megaparsecs. And now we go to the co-moving radial distance. That is chi sub s, and that is 1,984.7 megaparsecs. Okay. Now, we've got all the information we need to calculate the total mass of the lens itself. Let's take our next step is to go and using this equation, we calculate the distance from the source to the lens. So take chi sub s minus chi sub L, divide it by 1 plus the redshift of the source, 1 plus z sub s. And by the way, in cosmology, you see that factor of 1 plus z pop up over and over and over again. That is a normal feature, and you'll often see 1 plus z quantity raised to the second or third power, things like that for certain features. All right, so let's see what this is here. Putting in the numbers, I get, let's see, S minus L. So 1984.7 minus 1322.9 is 661.8, and I divide it by 1.523. Okay, so I get a number for that distance from the source to the lens of 434.5 megaparsecs. And I'm going to put that into the chat window and check to see that you got the same thing. If you didn't, maybe you should tell me, because it could be that I made a mistake. 434.5. Okay. Now we can put this into our, pardon me, our equation here. The equations that I put in a box are the more important ones. So here's equation 21.3. Our total mass in terms of 10 to the 12th solar masses, it's going to be 1.47 times the angular radius divided by 2. Now, our angular radius was 1.50 arc seconds, and we divide by 2 arc seconds. Okay, 1. To create a region. I will tell you that, hang on, the internet glitched again. I'll tell you, if you have trouble with DS9, this can also be done within the aperture photometry tool. A little more awkwardly, but it is possible. And I'll show you how you can do that as a backup plan. Okay, and it could be also that you have, you might need to go to the preferences, the settings for DS9, and to, unfortunately, it has a bewildering number of options there on the settings. But do check to see that what is it? I think it's called the cursor behavior, but when you click, that it creates a region, if you do a left click. And you can set that there. Okay, so D sub SO, that's 1,303.1 megaparsecs, times D sub LO, which is 999.1 megaparsecs, and we divide by 3,000 megaparsecs times D sub SL, which is 434.5 megaparsecs. Okay. And that's all raised to the first power. We don't have to change, there's no exponent on that. So let's take our terms, 1.47 times, now our second term, 1.5 divided by 2 is 0.75, and we square that. So we get 0.5625 is our second term, which is theta E over 2 quantity squared. And our last term, well, let's see here. We get our megaparsecs all cancel out. That's good. Now we just multiply two numbers and divide by two numbers. Let me enter that into my calculator. And I will note that I have created a spreadsheet for this. And I can upload that for you, send it to Priya, who can post it as a handy way of keeping track of those if she wants you to do that. 1303.1 times 999.1 divided by parentheses 3000 times 434.5. Okay, and we get a number which is very close to 1, 0.999. I like it when we get simple numbers that way. All right, so the number that I get for the mass, let's see here, 0.999 times 0.5625 times 1.47, I get a number which is 0.826. And that is times 10 to the 12th solar masses, because we multiply through both sides by 10 to the 12th solar masses. I just left it on the left to be kind of nice and symmetrical. Mass on the left, everything else on the right. So I get this number, 0.826, and I'll put exponential 12 for times 10 to the 12th solar masses. And check to see that you got something very close to that. Okay, now think about this. You have just from a single measurement, well, a single measurement of the picture, you have gotten the total mass of that galaxy. Or I should be careful. You have gotten the mass of everything within that ring. Which one are we using here? I believe we're using, let's see, -8. Oh, this is not in the picture here. Well, anyway, so you notice that the Einstein ring may have, it may circle the middle of the galaxy, and there could be gas that's light that's outside of that ring. And that's true. So we're measuring the total mass, stars, nebulas, dust, everything and dark matter within that ring. Okay. In order to
We lost your audio again.
our APT program.
Tim, sorry, but we lost your audio again. Sorry, you'll have to repeat.
Okay, thanks. I just saw the warning come up as well. It looks like it's delayed by a couple of seconds. So what we're going to do, the next step is we've measured the total mass. That includes both normal matter, stars mostly, and it includes dark matter. But now we want to subtract the amount of normal matter, and we will find the fraction of dark matter that's left. To do that, we need to measure the light from the galaxy. So normal matter glows, for the most part at least. So we open up the aperture photometry tool once again. And also this gives us an alternative way of measuring the radius, measuring the radius of the Einstein ring. Although now that I think of it, it is a bit more difficult to do it here. So let's open the image. Ooh, I've got to go through all of these here, don't I? Well, that's all right. Let's go to research. Research. Working the one that is the Hubble Legacy Archive, HLA folder. Within that, go for the one that has the F814 wide filter. Okay, and only one of these three files is an image. The DRZ stands for drizzled. That's when you have combined several exposures together. Okay, that's right. I forgot about this here. So we have, in a FITS file, you can actually have several images all in the same file. And they have what are called, I think it's called a header data unit. I think that's what that stands for, which is, again, or it's often called an extension. And so we need to choose which of these extensions, which of these images is the science image. Now, let's see. Usually there is an extension called that just says SCI for science, but this does not have the ability to pull that up apparently. Let's just take a look and see. Oh, you know what? There's a nice way of doing this here. So you see that in DS9, the science image came up by default, but there are those other extensions within it. If we go to File in DS9 and open as multiple extension frames, that will open each of the extensions in a separate frame, in a separate, kind of like a window in DS9. And I can use that as an easy trick for getting this out. HLA F814 wide. Let's see if it tries it. Yes, there it goes. All right. So what you see in this case, I've still got my original here. It displayed just the science image when I told it to display the image. If I told it to tell it to open each extension in separate frames, I get this one here is first one. You see it says SCI in the name, in brackets after .fits. The second one says WHT. That stands for the, I think that's the weight, and it tells you the relative exposure, I think, or the signal to noise. I think that's how that is. CTX is context. I don't remember what that means. And EXP is the exposure, the relative exposure time. Okay. WHT is a weighting image, and it tells you, I think it relates to signal to noise. Okay, so that means that out of the 1, 2, 3, 4 extensions, the first one numerically is the science image. Let's go back here. Now we get 2, 3, 4, and 6. Don't worry about which number it is. The first one is the science image. Okay, it's going to take it a moment. And I will note that the APT program does have a limit in the dimensions of the image it can display. I think it may be like 5,000 pixels on the side or 4,000 or something. And so you might have some images that are too big for that, and that's a drawback. But there are more sophisticated tools out there. All right, I am going to make sure we can find our, oh, there we go. Yeah, we can find that more easily here. So we're going to go and find our target. Okay, so use the scroll bars. And it was about in the middle of the right-hand side. Ah, there we go. Unfortunately, you cannot zoom all the way out with the APT program. All right, but you see that we have this here. Now, in order to see the, we need to be able to create an aperture which will cover everything within the Einstein ring. But we can't see the Einstein ring here, so we can make adjustments to it. So first, let's put the lower bound of the faintest pixels we want to look at. All right, so if you put your cursor over, wherever you put your cursor, if you take a look, values under cursor, this little section here to the far left, it gives you the pixel coordinates, and then below right ascension declination, and then below that, the pixel value in electrons per second. Remember, each photon creates a burst of electrons that are read into the amplifier. Okay, so if we take a look here, just outside the galaxy, I'm getting a pixel value of about 0.1, yeah, around 0.1. So let's put our lower limit as 0.1. I'm going to hit enter, but that doesn't, there, that changed it already. That's a little bit better. Now we need the upper value. Well, we've got to be able to see this better. Here I'm getting pixel values of up to about 0.3 or 0.4. Let's try 0.4 for the upper value. And I hit enter. Hey, that's much better. We could go just a little bit higher. I don't want to make it hard for us to see what we're supposed to be looking at, which includes where the Einstein ring is. I put 0.5, let's try 0.7. Okay, that's good. And now I can still, you need to make sure you can still clearly see the Einstein ring. All right, now I'm going to zoom in, see, magnify by 5. That may have been too much. Nuts. I forgot that when we do that, it tends to scroll back to the upper left corner of the image, and that is inconvenient. Oh, you know what? I think if I put the aperture, hold on. Okay, internet glitched again. I think if I click on our target, okay, if I click on our target and I put the aperture there, okay, like that, now when I go to magnify, to find the aperture, here we go, yes. Click on it. All right, and now click the button that says find aperture. Whew, all right, that's right. They did not completely make it difficult on us. So let's go and adjust the size of the aperture so that it is, we have it centered on the galaxy and we have it the size of the Einstein ring. So let me get back our instructions again. This point, we're going to be using let's see, I'll take you page by page on this so you can follow along on your own time after we're finished tonight, this morning. Okay, measuring stellar mass, section 21.1.4. All right, so we need to go to the settings. If you remember how we did this on the stellar, the globular cluster lab, we're going to do the same thing there, or something very similar to it. Okay, so turn to that page. That's page 127. It's the 7th page of the PDF. All right, we hit more settings, and we're going to get the photometry set correctly. The Hubble Space Telescope images, the drizzled images that you use for the science work, already have the sky levels subtracted. So we're going to use Sky Algorithm Model A, which is no sky background subtraction. All right. Let's see here. If you're using it from another source that may not have the sky removed, you can hit Model B, or probably even model F on there, depending on how much variation there is from one region to another. Model F will account for variation in different parts of the image. All right, the next thing we're going to do is to go to the way down here where it says magnitude 0 point. Now remember, the magnitude system does not have a natural zero. Zero magnitude does not mean no light. In fact, zero magnitude is very, very bright. So we need to know what is the reference, the comparison level for the magnitude for the filter and the telescope that we're using. So each telescope, camera, and filter combination will have its own 0 point magnitude. And for this, you really just have to look it up. I have looked it up for you. For the two filters that we're using for this project, really we just need the 814, but you've also got that 555, the green to yellow filter. It corresponds to what's called the visual or V filter. I've gotten you the 2 0 points there, and there is a place you can Google Hubble Space Telescope 0 points, and you put in the camera ACS and so on, and you can look up a much more, for anything that you come up with, you'll be able to find the 0 point on the web. All right, so we're going to put in 25.53 for that. 53, okay, down to a tenth of a 100. Things here. It snaps this magnified image to where the aperture is. And we need to go and make an aperture which is the correct size and shape for what we're dealing with. Let me repeat that. We need to make an aperture now which is the correct size for what we're dealing with. So we go to the big button on the right. Oh, you know what? One more thing. In order to see things better, there are more image adjustment controls, which I did not mention before, and it could be useful for these. You can change the stretch. Right now it's in linear. It's usually helpful to put a logarithmic stretch in there, although that seems to lower the contrast. But and you can make these adjustments. Okay. Stretch minimum, stretch maximum in a percentage of the range there. And the dynamic range. Often I don't know. I might not change that too often. Okay. Anyway, that's useful if you need to see better. So let's go to the big button on the right. This changes the size of the aperture. We're going to adjust the size of the aperture. We're going to leave it as a circle. Let me make sure that that's correct. Well, looking on the next page of my notes. All right. All right. Since we're looking at an Einstein ring, then we should have a perfect circle or something very close to it. You could have some cases where the light around the ring is a bit more stretched out, in which case you'd make an elliptical aperture. If you want to make it an ellipse, you uncheck this and you can adjust both the major and the minor radius. So major radius, and you can see how this thing is changing here. All right, but we're going to keep it circular. So we adjust the major radius, which is the radius of the circle, ease it out until you have it right on the edge of the Einstein ring. Now, a couple of things. We need to make sure that it is centered. And when we clicked on it before, it should have applied the centroid. If it didn't, then we can adjust that later. In fact, you'd want to adjust it now. You'd want to go back, center it on this middle of the galaxy, and then adjust the size of the aperture again. Okay, now the next thing is everything within this red circle is going to be counted as light from the galaxy. We do not want to include light from the Einstein ring itself. So let's back off just a bit. About like that there. And this gets us a decent compromise between missing light from the galaxy that's out here and including too much light from the lensing source. And that is a matter of, it may take a little bit of practice to get that just right. Okay, I'm going to apply that. Okay, we see it's made the adjustment out here and close the window. Okay, we have chosen sky model A, which says it is not going to make a measurement of the sky background and subtract that, and that's because that's already removed. So we, unlike our stellar photometry that we did a couple of weeks ago, we don't have an annulus around the aperture for measuring the sky background. So that is all just fine. I'm going to close that without making any adjustments to it. Okay. Now we just hit recompute photometry. All right, you may see a little blink, and what we want to find is in here in blue, the magnitude and the uncertainty. So the magnitude that I got, I mean, yours will be a little bit different if you chose slightly different radius for the aperture. So I got a magnitude.
We lost you again.
And to tell you the truth, 100th of a magnitude for something like this is, we have larger errors.
Sorry, Tim, we lost you again.
Oh,
sorry.
Okay. Am I back now?
Yeah, you're back.
Okay. So I'm giving it to 1/100th of a magnitude for both the uncertainty and the magnitude itself. But to tell you the truth, we actually have larger errors and uncertainties than the statistical error that shows up here. So that's a little more precise than we can really claim, but it's at least good to know what our magnitude uncertainty is. So we have a magnitude of 17.66 plus or minus 0.02. Now, what do we do with that? At this point, we've done all the measurements we need to do. Now we need to compute. So we need to convert from apparent magnitude into absolute. So for those of you who have already had several classes on astronomy, well, I guess in your first class, you would have already covered apparent and absolute magnitudes. When you're dealing with stars in our Milky Way or in any galaxy very close by, the conversion between apparent and absolute magnitude is fairly simple. And it simply depends on the distance. However, when we are dealing with objects at cosmological distances like this, we've got a little bit more work we have to do. Now, I have put this equation here, and I'll send to Priya a copy of my chapter 5, which goes over magnitudes and fluxes and so on, so that at least you see what I'm taking this from. But you'll find the same thing and maybe in slightly different forms elsewhere. So this equation I derive elsewhere. Apparent magnitude is the magnitude that we calculate based on the light that we see in the detector. In principle, you can get an apparent magnitude with no cameras, no instruments whatsoever. You can simply use your eye. There are skilled amateur astronomers who are quite good at getting apparent magnitudes of variable stars, for example, by using comparisons to them. All right, but you've always got access when you've got a picture of something, you can always get the apparent magnitude. We want to get the absolute magnitude, which is defined as what the apparent magnitude would be if that object were 10 parsecs away from us. It's just kind of a standardized distance, an arbitrary one, but it's a convenient round number. But in dealing with something that is very far away, the expansion of space causing that redshift makes some other effects. First, we have the geometric effect. The farther away it is, the smaller it will appear. And so we take what's called the luminosity distance, not the angular size distance, but the luminosity distance. And this is calculated, luminosity distance is the distance based on just plane geometry and the spreading out of light there. I'll tell you the truth, I'm trying to remember exactly how it's defined in a technical way. It's been a while since I've had to derive it. So I'll just leave it at that. Luminosity distance in megaparsecs. This 25 here, this comes about because our definition of absolute magnitude is based on a distance of 10 parsecs. But we're dealing with things that are so far away, it's ridiculous to deal with parsecs. We want to deal with millions of parsecs. So in the conversion between parsecs and megaparsecs and the logarithm, we get this factor of 25 that comes out. That's what we take 2.5 times the logarithm of those there and bring it out, and you get that 25. Two more items here. We have what's called the galactic extinction. That's capital A. I think I don't have the definition of this here. Oh, I mentioned it here. Galactic extinction. The dust in the Milky Way galaxy will dim the light of our source here, our lens. And so it will appear fainter to us than it would if we were in perfectly transparent space. So we have to look up the galactic extinction, which is how many magnitudes of dimming there are for an object which is in this direction in the sky beyond the Milky Way and with this filter that we've used. And I'll show you how to look that up in a moment. Finally, we subtract what's called the K correction, which is cleverly represented by the letter K. The K correction, this takes care of the cosmology, the fact that we have a relativistic space and we have an expanding universe. Because of the redshift of this galaxy, if we're using the near-infrared I band filter, the light that we're seeing with that I-band filter was not emitted as infrared light. It was emitted as visible light, and it was red shifted on its way to our telescope. So we have to account for the spectrum of the galaxy. If we want to know what is the absolute magnitude in the F814 wide filter, and that's the picture that the filter that we took this picture in, 814 wide, the I band, I'll just say for short, the I band filter. But the light that we detect in the I band filter was emitted at a shorter wavelength, a different filter really. So in order to correct it back to the I band filter, we have to use that K correction. And so people have spent careers in some cases calculating these K corrections, and it depends on redshift and it depends on the filter that you're using. I have given you, oh, you know what? I don't have it because it's in that other chapter, chapter 5. So I'll simply tell you what the number is, and I'll show you to you on the screen. Let's see. Observational astronomy book. Okay. And let's go back to chapter 5. Some of this should look familiar at this point. Okay, chapter 5, magnitude scale. All right. And this is a chapter that I will submit to Priya afterwards. All right, here we go. K corrections for elliptical galaxies in the I band or 814 filter. So we have to look up the redshift. We have to know what kind of galaxy it is, because those will, a spiral galaxy or an elliptical will have a different spectrum. We look up the redshift. This is the redshift of the lens. Our redshift of our lens was 0.332. Okay, so our closest value is 0.35, and really you should interpolate. And so we're going to put it down, we'll round it off to a K value of 0.27 magnitudes. Okay, so that write that down as K. Notice that the values are 0 at a redshift of 0 because there's no redshift at that point. And they tend to increase as you go up in redshift, but that really depends on the actual spectrum, exactly what it does. Some of them go negative for a while. Okay, so we've got K, we need to find A. Now for that, we go to the NASA Extragalactic Database, which we might have gone to before, I'm not sure, but I'm going to give you the link in the chat window right now. So go here. Now, if you have an object that has a catalog name, you can simply put it in here. In this case, we've got a lens, which this is not, the name that we've got on this lens is probably not going to show up on any normal catalog, but we do have coordinates for it. And we need to find out how much dust there is in the Milky Way galaxy in that direction. So let's go and look up the right ascension and declination of this thing here. Okay, and we're going to go to ONNED Tools, go to Extinction Calculator. All right, what kind of coordinates are you putting in? J2000 is the equatorial coordinates set at the position of the North Pole, the axis at the year 2000. Now we've got to put it in. You've got to put H between hour after hours, M after minutes, and S after seconds. So I'm cutting and pasting. So H for hours, M for minutes, and S for seconds. And now I'm going to do the same with the declination. Be careful when you copy and paste about the negative signs. Yeah, the negative signs sometimes show up as different symbols, longer dashes or things, and you have to retype it. D for degrees, M for minutes, S for seconds. And we hit go. And it is picky with the syntax. Okay. Now it comes up with a table filled with filters. We want to look for the Hubble Space Telescope first. Let's find out. So it gives us just camera name. We were using, and you can find this in one of the headers in the FITS file. It'll tell you the camera and the filter combination. We were using the advanced camera for surveys. Oh, it's in the file name. Here we go. Instrument ACS. And let's see here. ACS, okay. And our filter is 814 wide. There we go, 814 wide. Well, we don't need to check it because we're not doing anything with that. Central wavelength is the first thing, galactic extinction in magnitudes. 0.057, so write that down. Okay, that's not very much. It's less than 1/10 of a magnitude. Okay, so now let's take a look at our equation here. Okay, so at this point, it's back to the calculator. So our absolute magnitude is the apparent magnitude. That was 17.66 minus 5 log. Now, this is the base 10 logarithm, not the natural log, times the luminosity distance. Okay. In the instructions, in the printed instructions, I tell you to record the luminosity distance. When we were doing it tonight, I didn't tell you to do that. So I've got to bring back the cosmological calculator. I'll put that back in the chat window. Okay, let's see, our redshift for the lens was 0.332. I hit general. Yes, 332 is there. And I look up the luminosity distance. So that is 1762.1 megaparsecs. Okay. And we divide that by megaparsecs, so we get a dimensionless number, 1762.1. We subtract 25, that converts us to, keeps everything in megaparsecs. We subtract the extinction, that was 0. Big thing is 5 times the logarithm of 1762.1. Okay, so I've got 17.66 minus 16.23. That's my second term. Minus 25 minus 0.057 minus 0.27. And I get negative 23 point, rounding it off to 2 decimal places, 23.90. I'm typing that in the chat window. Check that because I could make a mistake. And see if you get the same number or very, very close to it. Again, if you had a slightly different magnitude, you will get a slightly different number, but it should not be a very large difference. Maybe in the tenths of a magnitude. Well, hopefully not too many tenths of a magnitude. 7/10 of a magnitude is about a factor of 2 in flux, in brightness. So we want to keep those down to small changes there, small differences. Okay, well now we have an absolute magnitude in our chosen filter. Now, the last, well, not quite the last step, the next to last step is to calculate the stellar mass. Again, I use a cursive M for mass, so we don't confuse it with magnitude. Okay, to convert from our brightness, our magnitude to a mass requires some other research, which, well, thankfully other people have done for us. And this is called a mass to light ratio, or M to L. L in this case represents luminosity, which will be in ergs per second. But we're dealing really with magnitudes here. So what I've done is I've taken this and I have converted it into a magnitude form. Now, I've got a footnote here. I used a paper by Zibetti in 2002, who gives the near infrared mass to light ratios in for certain kinds of galaxies. So he has mass to light in the H band. That's farther into the infrared than what we're using. But he gives it as 1.23. So what you're going to do then, if you can't find a mass to light ratio for the filter you use color conversions, filter conversions. So I took elliptical galaxy colors from another paper on elliptical galaxies, Manucci 2001, and I took, all right, here's the magnitude we got in the I band. What is a typical color for an elliptical galaxy in the infrared? And Manucci's paper gave me the I to H conversion there in magnitudes. Okay, so that's what I've got here. This is a color term there. So there's a little bit of extra work that went on behind the scenes, but there are papers. You would look in the abstract of the paper for galaxy colors, things like that. Okay, let's see. So 1.23 That's the mass to light ratio in the H band, times, now we've got to convert luminosity into magnitudes. So we just take the magnitude equation and we solve for the luminosity. Okay, so we've got 10 times 10 to the negative 0.4 power. That's 1 over 2.5. Let me make sure that that's right. 1 divided by 2.5 is, yes, 0.4. And that 2.5 times the logarithm of the luminosity, that's where we get the 0.4. Negative because it was in the denominator. Let's see here. Now we've got the magnitude in the filter we chose minus, oops, minus 5.19, and that comes from the conversion of the color of the galaxy from I band to H band. And then we're in solar masses. Okay, so that mass in stars, the mass of the stars, that's what the asterisk is for, is 1.23 times 10 to the negative 0.4. Okay, our magnitude now, that's negative 23.90. We subtract 5.19. Okay, so our exponent, the whole thing in the exponent, let me get a calculator out. Negative 23.9 minus 5.19 is negative 29.09 multiplied by negative 0.4. That gets us positive 11.636. Whenever you deal with exponentiation, it's good to keep an extra decimal place or so before you come to the final answer. So now we've got 10 raised to that power, 11.636. Okay. And we multiply that number by 1.23. So I get an answer, which is 5.32 times 10 to the 11th power solar masses. I'm typing that into the chat window. And we're almost finished here, which is good because we're about out of time too. Stellar mass is 5.32 times 10 raised to the 11th power solar masses. And I'm putting that in the kind of computer form, 5.32 E11, but that means times 10 to the 11th power. Okay, and again, you should get a number somewhat close to that. Phew, all right, already that's been a lot of work on the calculation. But we've got one last step, and that is we want to find out, we found the total mass of the galaxy, we have found the stellar mass, now we want to compare the two. So what did we get for the total mass? I'm actually kind of asking, what did we get for that? Here we go, here we go. We've got 0.826 times 10 to the 12th power solar masses. So that is 8.26 times 10 to the 11th power solar masses. So, all right, first of all, a sanity check. We should have the total mass, which we calculated through the Einstein ring, be larger than the stellar mass, which we calculated from the light. And sure enough, we have stellar mass of 5.32 times 10 to the 11th, and a total mass of 8.26 times 10 to the 11th. Now let's just divide one by the other. Hang on. Now we just divide one by the other.
Don't you subtract?
Oh, yes, you're right. Well, it depends on what we want to do. We can subtract to find the dark matter, or we can divide. Oh, actually, no, wait. We still have to divide. We still have to subtract. You're right. And then we can divide to find the fraction of dark matter. So if we take and we say that the mass in dark matter, m sub dm, is the total mass minus the stellar mass. That is 8.26 minus 5.32, and all of that's times 10 to the 11th power. Eight point 8.26 minus 5.32. Okay, so that's 2.94 times 10 to the 11th power solar masses. And now we can divide that by the total mass in order to get the fraction of this, which is dark matter. Okay, so here, let's see here, 2.94 divided by 8.26, and I get 0.356, so that's 35.6%. Now, that number is a little low. That number is a little low. We would expect something to be much higher, close to 90% or something like that. The imperfections come about because probably in the mass to light ratios or the colors or something like that there. I have consistently gotten numbers usually which are a bit low with this technique. But we're doing aperture photometry rather than fitting a model, and we are only looking at the center of the galaxy rather than the entire galaxy. And that's because when we look at the mass, the total mass measured by the gravitational lens, we only can calculate the mass that is within the lensing ring. Mass that is outside that ring simply does not affect it there. Let's go to the first one here. There we go. So you're not getting a complete picture of it with this, but it is a kind of a quick way. And well, to tell you the truth, you're still probing. You're doing a lot of this correctly, but you're probing the dark matter content of the center of that galaxy and along the line of sight to that galaxy as well. So the dark matter in the outer parts there will be different. And also your stellar mass to light ratio can change a bit from the bulge of the galaxy to the outer parts, but I'm not really sure by how much. So this is still an area of ongoing research there. Now, so you've got a list of other galaxies, which are all done with the same proposal ID number. And if you go back to the MAST archive and you search for others in that, and for that matter, for any gravitational lens that you come across, you can do this technique. There is more work involved with it, though, than the earlier projects I had given you, because you have to look up the lens and source redshifts from the paper, usually from the paper, and you have to get the mass to light ratios for the kind of galaxy that you're using and the K correction for the kind of galaxy you're using. So if you stick with that one proposal, then at least you have pretty much the same information. But if you go find one on your own, you'll have to look up a bit more. A final note in measuring the lensing part of it, though, you can get a lensing measurement of the entire galaxy rather than just the central part. Let me get rid of this region here and show that. Okay. So see, our galaxy extends out pretty far. I'm adjusting the brightness and contrast so that we see the outer parts of it here better. But we're only measuring this middle part here. And by the way, that light there, I'm not sure, but that might be a bit of lensed light as well. Well, if you go to one of those gravitational lenses from the early studies that I showed you here. Okay, there, Kevin Ratnatunga's paper. Okay, if you look up his, you see that the dots from the source, the images of the source, are pretty much outside the visible extent of the galaxy, which means you're going to be getting most of the galaxy in that case. And in that case, you can use this technique, but you see that you don't have an Einstein ring. However, the dots here will pretty much bracket the Einstein ring. These will be out, let's see here. You've got outside and inside. You'd want to use an elliptical measurement of that there. I'd have to think about that a little bit more. Priya has a comment here. If we used GalFit to model the luminosity profile, we could get a better estimate of the stellar light. Yes, yes. And that would affect the stellar mass as well. And that would improve this quite a bit. The actual paper that was that did this, in fact, did use GalFit to measure that. I believe I've got the paper here. Let's see. That's tonight's work. Let me find my other page. Bolton. Here we go. This is the paper. Unfortunately, I got it before it had been published in the journal, and so I have an early version that does not have the reference in it. But the Sloan Lens ACS survey. I'll put that in the chat window here. And I think it's the year 2006. You can look that up in the NASA, the ADS, the Abstract Database Server. And they show you how they did it. And they've got a longer list of their targets. They did more than one proposal with the Hubble to get these done. That's the spectroscopy there. Let's get to the images. Here we go. So here you see how in the first picture in the upper left, they've got the 814 image. And then, as Priya mentioned, if you use GalFit, that will allow you to make a two-dimensional model of the galaxy to the image, and you could subtract it then. You would need to mask out everything else within that, but you can model the galaxy and mask it out and model it and subtract it, and you'd see whatever's left over. But importantly, the model will tell you the total magnitude, the apparent magnitude, and it will do it more precisely. And so in that case, now that will, to tell you the truth, that will tell you still the total stellar light of the galaxy, rather than the stellar light within the elliptical, within the ring aperture. We'd have to take a look at the paper again. It's been a while since I've read it, but they do, I believe they mention how to get the best mass measurement, the stellar mass measurement for this here, so that you're comparing.
Your audio is gone.
Does everyone hear me now?
Yeah, yes.
Okay, good. And they do it with the shorter shorter waveband filter, shorter wavelength filter here as well. So you've got a color image of those.
But Tim, did they get what their values different from what you just got? Because I can see our sources there, right? The source that
Yes, let's take a look and see the results here. It might be in a separate paper, but let's check to see. It might be in this one. This is the first out of a few different papers they published on this. It's almost to the end of the paper. I think it's in a separate paper. Let me see if there's a table up here.
I think they've used this to just describe the methodology and the data.
Yeah, and the observing data. So they give the redshifts here. So this is where you get the redshift for them, the source and the lens, but they don't give the mass results on that there. So, but that it is in one of their later papers.
Okay, we can check it out.
Mhm.
And another
So
thing
now,
is,
go
yeah,
ahead.
how accurately do we know DSO and DLO? Couldn't there be some other
Those,
factors causing the lensing?
so the, so we get those purely from spectroscopy.
Okay.
And so we can get those very accurately. They've got it quoted to four decimal places. Well, but although they do have, I guess there's probably some uncertainty on that there. But they at least quote 4 decimal places. I would certainly trust it to 2 and probably 3, but they show the spectra where they measure those from. And so
That's fine. Those
once,
factors are fine, that means. Right?
and the mass that you come up with does, however, depend on the calibration, or it depends on your assumption of a cosmological model. If you were to assume a different value of the Hubble constant, which there is some debate on right now. 72 is one popular value. 62 for a while had been another popular value. So you had a difference of several percent right there. You would get a different mass. The stellar mass would not change as you do this, but the mass you get from the lensing would change. And so that's an important thing too. Actually, well, hold on a second. The stellar mass would also change because the conversion from apparent magnitude to absolute magnitude
Mhm.
also depends on the Hubble constant there.
Yeah, that's true.
So I'm not entirely sure how much it would change. The ratio would change if you assumed a different value of the Hubble constant.
Mhm.
It's not immediately obvious to me.
Right.
So this is one which is a little bit less cut and dried as a project because you have you have several things that you have to make some decisions about on it here. But I think that does make it kind of fun. Plus, you get to look at really beautiful pictures with these.
Uh-huh.
And and uh, when you are looking, whenever you're looking at one of these images from the Hubble, don't just, I mean, sure, take the data that you're supposed to do for your assignment, but take some time to look around it. And you realize that in this image, there are probably hundreds of galaxies. And very few of them, I mean, none of these have been seen by more than just a handful of people ever. You'll be one of the very few people who's ever looked at that galaxy, for example. It's not something that people have studied very much. It was not the subject of the survey, but it's a gorgeous galaxy. It's a barred spiral. It has
We
that
lost your
look
audio
like.
again.
Oh, the two galaxies up here, which appear to be merging, are also just a beautiful example. Take some time to look around. Because, and I should show you all this. This is another example of lensing, and I'll leave you with that point. Because you sometimes come across something which is,
Tim, we've lost your audio again.
oh, shoot. Okay, can you hear me now? Can you hear me okay now? Anyone hear me? Oh, okay, good, good. Thank you all. Let me show you something I came across from here we go, mystery object. That should give you a hint as to what I'm, what I'm finding here or what I'm not finding. So some colleagues of mine and I we had a proposal with the Hubble to take a look at a quasar. And let's see here, images. So we were looking at a quasar, and our goal was to take a look at the galaxy that hosts that quasar. So quasars are an active galaxy. They have They have a black hole at the center, which is actively sucking in gas and dust, and it glows and it produces this bright glow, which we can see from billions of light years away. All right. Now, the quasar we're looking at was right just a little bit off center there. Let me make the bright side a little bit brighter. Okay. There we go. So here's our quasar. Okay, now that it took a bit of work. Was that the quasar? I think that was the quasar. That took a lot of work to see anything behind. Maybe it was this one here. It's been a few years and I've forgotten. All right, and we can make out a little bit of fuzz around that, and we can make the galaxy out there. But while I was at this, I took a look around the rest of the picture. And what's interesting is take a look at all these other dots. These are galaxies too. There are very few stars in this picture. There's actually, I think it is this one here because there are those um, diffraction spikes, which we see from only stars or quasars. And looking around, all of these are galaxies. And you see that there's some extended light. This is actually a galaxy cluster over in all over this part of the field of view. Well, that was pretty neat. And when I looked more closely, I saw something which you don't normally see in these. That. Now, this took me by surprise, and I showed it to my collaborators. None of us knew what it was. It has the appearance, well, it has the appearance of straight lines. It has a line of symmetry here. You have two blobs here, and then this straight line, that dashed line, and this dashed line. So it doesn't look like a spiral galaxy. A spiral galaxy could have arms, but they would be twisted. Maybe it's a galaxy, a merging galaxy, in which case maybe there are some kind of shocks as the galaxies collide, but that should still have a curve to it. We considered that it could be a protoplanetary nebula, which can have outflows that look very straight. But we calculated the magnitude and the distance it would be, and it would turn out to be well outside the Milky Way in a place where we just would not expect there to be any planetary nebulas. Finally, we settled on it being a gravitational lens. But you've seen pictures of these gravitational lenses. They don't tend to look like this either. With a gravitational lens, you tend to see a lensing galaxy in the middle, usually a big elliptical like this one here, or that there, or that there. And then you see arcs distorted around it, or just dots. If it's a quasar, that's the source. And here we see different shapes, again, straight lines. Where would the lens be? If the line of symmetry is here, so you should have the lens be a line like this. But that doesn't explain that line, that dash, these blobs, or that line. It turns out, though, after a good while of working on it, this is being lensed not by a single galaxy, but rather the lens is this entire cluster of galaxies, which is at a redshift of about 0.5. When clusters act together, they can produce very complicated lensed images. And this had not really been fully understood. I guess we still don't fully know it until some of the lensing surveys came out, the cluster surveys came out with the Hubble, in which they were looking at very deep images at a large number of clusters at the right redshifts. And they started seeing a few of these kind of odd, sort of symmetrical shapes in one or two places. There are not many of these, though, that are known that look like this. And what's happening is that you don't have a lens in the middle here. You've got a very complicated shape of where the images will appear as you go from a mass concentration here to here to here to here and so on. More recently, some other astronomers have taken pictures of this. And we got to get a paper out before we get scooped on this thing. And let's see, images. And combining those together, I can get a color image of this. This is rotated now. But we see that we've got bluer light on parts of it and whiter light here. So I've combined three images to make a false color red, green, blue image there. So this tells us that this is probably got heavy star formation in one edge of it, but we still don't really see the structure. Um, we see structure, but we don't know what it would look like closer up. I've smoothed it out a bit and adjusted the colors here. I don't know, I think that one's better. So we're working on following this up. We don't know its redshift, but it looks like the models show it to be a spiral galaxy at a redshift of about Z of 1, more or less. But when we do the photometry, it matches something that is a bit closer by. So it's still up in the air as to exactly what this thing is there. But this is some really interesting stuff. And this is the kind of stuff you can find by chance if you just look around in the pictures a bit more. Okay, I'll end the lecture with that. I believe I went a bit over time though. Any questions?
I think the chat window has. Yeah, no, there aren't any questions.
Okay.
Yeah, please post questions. Oh, Tim, that was a very interesting session today. And I think I really liked it that, uh, obviously in science, people have this false thing that everything is sorted. And it's
Right.
really, yeah, but it's definitely not. But that's something really strange, that lensing kind of an effect. The
Yes.
straight lines is what is the most scary thing, I think.
Oh, I do see a question here, Gitanj. How do we differentiate between lens light and galaxies nearby? That can be a problem. Sometimes these things, there will be galaxies that simply look like they're lensing because they happen to make an arc around a red elliptical galaxy, but they're not. It happens to be like that. And so in some cases, you have to use some judgment and experience on these. You might say that you have a lens candidate, and then you would look to see if it would follow. Well, the in strong lensing, the curvature of the lensed image will be along more or less along a contour line of the mass distribution of your lens. And so if you take if you draw lines at right angles to the shape of your of a thin arc lens, it should point inward to the heaviest concentration of mass. So that's what you use to find your best candidates. But sometimes you would find a galaxy. Let's take this for example. Maybe this one here. See this little faint one here? That one is kind of linear. All right. How do I know that that's not being lensed by something else in this cluster? Well, it could be distorted heavily, stretched out, and it's so short I can't tell if it's an arc or not. What you would look at would be to see if there are others nearby that which are also arced in the same direction. And you can have what's called weak lensing if you have not much distortion of the shape, but simply the elliptical cross sections of the galaxies, whether they're spiral or elliptical galaxies, doesn't matter. If they line up in the same direction, more or less, in a region, that's an indication of what's called weak lensing. And by the way, strong lensing will distort the shape more noticeably. And if you look in this color picture I have here, there are some very faint blue streaks in a few places. And I believe that those are more examples of some strong lensing, maybe from the same galaxy that produced this, maybe from some others. We don't really know until we get a spectrum. But that there could be part of the same thing. If you have multiple images, check the color, and but really you should check the spectrum. If the lensed images will all have the same redshift, and that's a way of absolutely telling. Um, Ayush says, could you explain the occurrence of diffraction spikes for stars and quasars and not for galaxies? Yes, certainly. So the diffraction spike is a feature of telescopes that have struts that hold the secondary mirror in place or extra mirrors in place. So thinking back to diffraction, if you have a slit opening, you will get a diffraction spike that is perpendicular to the slit. If you have a circular opening, like for example, the mirror, the primary mirror itself, you will get a ring shape and you'll get a disk in the middle, which is called the Airy disk, AIRY, named for the British mathematician. So, and then there's the Airy function that describes it. And that's because you're getting a perpendicular streak at every point along the rim of of the telescope's main mirror. Uh, so for example, the James Webb Space Telescope, which will have hexagonal sections of mirrors, will have a diffraction spike, 6 diffraction spikes, one for each direction of of a mirror, of the edge of the mirror. Now, every point of light that comes from your sources, no matter what they are, will have the same diffraction pattern when it arrives on the camera chip. However, the streaks, the diffraction spikes, and the airy rings, if you have a circular pattern, all of those are fainter than the middle of the image, which will be where most of the light is concentrated. So if you have an extended object like a galaxy, which is relatively, let's take this one in the upper left here. Let me find it better. Okay. There we go. That's much smoother. All right. So this galaxy, well, hold on. Can everybody hear me again?
Yes, yes, we can.
Okay. This galaxy, well, all galaxies, for the most part, get brighter in the center and they're fainter on the outer edges. Okay. If we had, let's take this one on the lower right here, which is more or less evenly bright. It's an edge-on spiral, probably. Every pixel here is surrounded by the diffraction rings, the airy rings, and the diffraction spikes. But the pixel next to it is about the same brightness. So its diffraction rings and diffraction spikes are shifted by 1 pixel from the one to the left. Then you got one to the right again, and so on like that. So because you have all of these pixels at more or less even brightnesses, then the diffraction rings and the diffraction features blur out and you don't see them surrounding the galaxy. On the other hand, if you have and even here in this galaxy, which is clearly brightest in the middle, you'll have a bit more of diffraction rings and spikes from the pixels at the very center, but you still have a lot of light from the pixels around it. And so they are blurring out those diffraction patterns again. Now, let's go to a star. This is a star. Okay. As I said, we have diffraction rings. You see that here. This is the airy disk in the middle and surrounded by the first airy ring, diffraction ring. That's from the circular opening of the telescope and the mirror. The diffraction spikes are perpendicular to the struts that hold the secondary mirror in place. Light diffracts around it. Okay, this is an unresolved point of light. The light would ideally, if we had no wave pattern of light, if it were just geometric rays, would be coming from a spot less than 1 pixel across. So what we're seeing here is purely the diffraction pattern itself. So imagine every pixel of light being surrounded by this exact pattern, and it's called the point spread function, or PSF. Everything in astronomy is an acronym, it seems. What you do is you convolve the idealized image, the undiffracted image, with the point spread function for your telescope and camera. And you create, by doing that, optics creates the real image that you actually see here. Now, if we go to a quasar, this is our quasar here. Now I'm pretty sure of this. Notice that we have a point source with a strong diffraction spike and a diffraction ring around it, surrounded by a resolved image. We see a broad region of that galaxy there. Okay, and I'll just show you that all of that here is galaxy. That's not diffraction pattern. Okay, so this is what a quasar looks like. We have the central few pixels here from the quasar, which are surrounded by light, which is not nearly as bright. And so the diffraction pattern for those bright pixels in the very middle stand out above the much fainter and spread out and blurred out diffraction patterns from all the pixels spread around here. So we've convolved the idealized view of this galaxy, which is a broad region plus one bright pixel in the very center, or maybe two, with the diffraction pattern, the point spread function, and we come up with this here. So all stars will show a diffraction pattern if they're bright enough. If they're too faint, maybe this little dot over here is a star, I don't know. We don't see the diffraction pattern simply because there's not enough light in those spikes to show up for that very faint star. But if it's a galaxy, even a bright galaxy, it will blur that diffraction pattern out and you simply won't see it. And that's a way of telling quasars and stars from normal resolved galaxies. I should say that there is a very slight exception. If you have a very sharply concentrated galaxy and you have a very wide diffraction pattern, like what we do in the infrared, which is this image here, you may find weak diffraction spikes from the core of a galaxy, but it will not stand out like the quasar does. Okay, Sargam says, is there any role played by dark matter in gravitational lensing, and could it affect the light that reaches us from distant galaxies? Yes, in fact, that is, I should make that clearer then. That is why we're able to measure the dark matter with this technique. So dark matter has mass, normal mass. It's not any, it's the same, it's not normal matter, but it has mass in the same way that we measure stellar mass and so on. So the effect of the dark matter's mass is the same as the mass of stars. If you had a trillion solar masses of dark matter or a trillion solar masses of stars, you would get the same effect in the lensing. So the lensing measures the total mass, but only the stars are visible and the gas clouds and so on. So when we use the mass to light ratio with the photometry, we get only the stellar mass, and maybe it's corrected for dust and nebulas and gas and so on. And when we do the lensing, we get stellar mass plus the dark matter. So that's why we had to subtract one from the other. Okay, anything else? Okay, John says, speaking of the exoplanets, what opinion do you have of the techniques with gravitational lens? In fact, um, I've mentioned strong gravitational lensing and I mentioned weak gravitational lensing, but I did not mention what is called the weakest of all. Well, it's not really yeah, I guess it's the weakest of all, called micro lensing. And that actually is used, that's what John is talking about here, that is used in detecting certain kinds of planets. Now, um, the idea is, I'm going to pull something up in another window. It's from my astronomy class there. Uh, the idea is that if you look at a field of stars, let's pretend these are stars right now, and you just keep taking pictures hour after hour, day after day of those stars there, um, you'll find that if one star lines up with another star very, very perfectly, then for just a few hours, the gravitational lensing of the nearby star will, well, you won't see multiple images of the distant star because the distances and the masses are simply too small to split that image into multiple resolved images. It's just too small an angle for us to resolve. So you don't see multiple images of the background star. What you do see is the background star is magnified. Now, well, it's not resolved, right? So it doesn't look bigger, but instead it becomes brighter. And as it grows brighter, as the star, let's say a little wandering star goes in front of this one here, as it lines up, the background star gets brighter. And then as the lensing star moves on, it gets dimmer again. And you get a spike in the brightness over time like this. If that star, the one causing the lensing in the foreground, if it had a massive planet around it, then the planet would also do um, it would also do some gravitational lensing, and you would get a second smaller spike. So you'd go see it going up like this. It would come back down. That's the spike from the star. And then you'd see a little up and down hiccup like that, a little tiny spike as it came down. And you could use that to measure the mass of that planet. As it happens, this week, there was a discovery, or the announced discovery, of an roughly Earth mass planet that had no star, and it was discovered with microlensing. That's called a rogue planet. And I'm trying to find, let's see here, the press release from this. Let's see here, news, most recent. Okay. Oh, wait, here it is, Universe Today. That had a good article on it. And I'll,
You need to share that. Okay.
and they have intersecting orbits. And hold on, I had the sound called out again, kicked out again.
Yeah.
Early in the formation of a solar system, the planets' orbits are not stable. They often intersect with each other, and that can bring some planets closer to each other to where a more massive planet can add energy to a low mass planet, and that extra kinetic energy will kick the smaller planet completely out of the solar system. So we predict that there are so-called rogue planets out there in space which have been ejected and do not have a star. In fact, if you consider a planet to be the definition of something which is orbiting a star, well, you might not even say that that's a planet at all. But I think if we talk about something that's smaller than a star, then planet is still a viable name. So how would we ever find them? They don't glow enough for us to see, but they do have mass. And so if it's got enough mass and it lines up perfectly with a star, we can detect it with microlensing. But the chances of anything ever lining up perfectly with a star are very small. So you have to take pictures of clusters of stars so that you get a lot of chances of these here. And this time there was the OGLE, that's the optical gravitational lensing experiment, in connection with the Korean microlensing telescope network. They collaborated together and they detected this one here. Now, the theories say that the ejected planet should be between a third and one Earth mass. And I don't see if they told us what the mass of this rogue planet is here. Nope, I don't know that they gave the numbers. However, it does say that they found several. They found, oh, sorry. They have found several through microlensing. This one had 15 data points total. So that's not a lot to fit the data to, but it's enough that they say that corresponds it corresponds best to a smaller planet, and it does not correspond to the pattern you get from a stellar flare, which could also make the star go brighter for a few hours. So anyway, I think that's a fantastic technique, and they've even there's been one claim of an exoplanet moon that's been detected this way. So I think that is yeah, it's a good technique, and it's still there's the question of exactly how you fit the models, but that's true for all of the work we do. Pi Planet, I haven't heard that name for it, but that may be. That's a little outside my field, though. Okay. Oh, and John also asked, what was my experience using the Hubble telescope photos for the research? That I started off using the Hubble as a graduate student. I did all of my dissertation work on it, but they warn you in the user's manual to the Hubble, and there is a user's manual. It just seems like any old piece of equipment or software, right? Um, not to put in a proposal, an observing proposal for your PhD dissertation. And the reason is proposals only have about a 1 in 10 chance of being accepted. It's tough to get it through. I've only had one in the last few years. last several years, to tell you the truth. Um, so I did all of my dissertation work with the archival data. So this workshop that y'all are in on how to use archival data, this is ideal because you have a wealth of information, and any picture that has ever been taken with the Hubble is available for you to use free of charge, except for those in the last 6 months to a year. There's still the people who proposed it get to use it exclusively for up to 1 year, and after that, everybody gets to use it. So that way you've got a little time. If you put in the work to propose it, you've got a little bit of time to use it before anybody else can. But after that, everybody can. There are, I don't know the number. I'm sure there must be millions of photographs in the archives, and you can look at any of them, every one of them. Uh, so it was fantastic. Even though I wasn't telling the telescope point here, now point there, I was still using it. And it's really thrilling, especially when if you visit the United States and you go to Washington D.C., the Smithsonian Museum. There's a network of museums. These are all free. Most of them are in Washington D.C., and the Smithsonian's Air and Space Museum is my favorite of all of these. Go into it, and one of the rooms, they have a full-scale engineering test model of the Hubble Space Telescope. It is about 30 feet tall. What is that, 10 meters or something? It's enormous. And I had been working on the Hubble for about 1 year before I made it into that room. And I did not realize how big this telescope was. I thought it was much smaller. And you're staring up at it, and your neck is getting a little sore from craning all the way back. And you realize that there's that one little cabinet up there, halfway up, which is the camera that you use. And you realize that's your camera there. Well, this is still the prototype model, the real one's in space, but there it is. Now, in fact, they have retrieved the camera that I did my dissertation with, the Wide Field Planetary Camera 2, and brought it back, and it's on display right next to that now. In fact, they've got little holes cut in it because they were measuring micrometeoroid impacts and what damage they cause over the several years it was up there. So I actually get to see the camera I did my dissertation with. Now, I'm doing also from ground-based telescopes, and it's actually harder to do because the atmosphere is in the way and it's blurry, and they don't calibrate your data for you. You've got to do all this stuff yourself. It's more work. I really got spoiled using the Hubble from the beginning. Probably it's best if you use a ground-based smaller telescope and learn to do all this stuff yourself, and then you go to use the Hubble, and it makes life easy for you.
Yeah, and Tim, I would like to butt in that
Yep.
yeah, even I have used both Hubble as well as ground-based data. And one other very important thing in support of archival data is it's the best quality data, right? With
Yes.
your ground-based
Yes.
telescopes, you're not going to get that quality of data that you're getting with Hubble, which is already there without writing proposals and without
Right.
having to face rainy nights and suddenly you go and there's no data available because it rains or it gets cloudy or something like that. And here you have the advantage is access to the best of the quality of data you could get, right? And I
Yes.
think that's so after doing a lot of ground based, you realize that instead of writing proposals, why not just work with archival data where you know what you already have, right?
Right.
I think
And
both have their fun, but
if you've
yeah.
been used to doing some of these Sloan Digital Sky Survey, where you might not even use the image, but simply go to their catalog, the
Mhm.
database, where they've got the magnitudes already measured for you and calibrated and such. Well, the Hubble has done the same thing now. This here is the Hubble source catalog. I'll put a link
Yes.
in the chat window. And this is Hubble's version of doing the same thing. Now, there is one drawback, and that's because while the Sloan is looking at a well-defined section of the sky, and it's using the same 5 filters for every single observation and the same exposure time, the Hubble is driven by proposals. And so it looks over here, then it looks over there, and it looks somewhere else. And you're not covering the whole sky, and you're not covering even a unified part of the sky, and you're not even using the same filters or cameras from one observation to another. But you've got, as Priya mentioned, the best quality data that's out there, the absolute best quality telescope data that has ever been taken and will ever be taken until the James Webb space telescope um, goes up in hopefully in one more year. So you can use that, and there are some great projects you can do with the Hubble source catalog here. So that's another thing to delve into. Color magnitude diagrams you can do with that as well.
So does the Hubble source catalog include sources and globulars and stuff like that? The one that
Yes,
you
it
did?
does. In fact, there is they have a project example
Okay.
page. Let's see here,
Wow.
interfaces. Let's see here, Python Jupyter
The
Notebook.
detailed
That's
use
on the
cases and videos of
yes, detailed
yeah.
use cases. Okay, and at least one of those is using
Yeah.
um,
Wow. M87. There's one
M87.
M87
Where was
for
that one?
SMP.
Yes, yes. Color
Wow.
magnitude diagram for the small Magellanic Cloud, globular clusters in M87. There's another one for some Milky Way. Here we go, globular cluster M4.
M4. Mm-hmm.
Yeah. So they've got a few examples like that.
Okay, wow. It's very nice.
Yeah.
I This is very nice. I do have something with M4. I should check that out.
Uh-huh.
Yeah. Wow. So I'll add this to our thing.
Mm-hmm.
Yeah, and then participants are obviously most welcome to think up their own projects. I mean, while you're hearing, and if you can think up something of your own, that's even better. And we'd obviously encourage that. So, Tim, I'd like to thank you very much. Thanks so much. It was so nice having your
You're welcome.
sessions, especially
You're
the way
welcome.
you patiently did it was was a new exercise in teaching for me. I mean, I've been teaching, but you've been doing it so patiently with every little thing being explained, and I think that's really nice. So,
I'm
thanks
glad
so
y'all
much,
appreciate that.
and we really enjoyed having you over, and I'm sure
Well,
all the
you're welcome,
students
and
would
I
agree.
certainly
And
appreciate your invitation to do this, and it gave me a chance to work these out a bit more. And you're asking that, so the chapters that I've been posting to y'all have been sections from a book that I'm writing, but I haven't really written much in the last 2 or 3 years, and so this gave me a bit more incentive to go on and do that. So if people have suggestions for projects that would be good to put in, those are things that I might contribute to it. I'd like to that I might add to the book because I'd like to have a wide variety of types on there. So I'll take any suggestions from people.
yeah,
So thanks again, and I will post that the other chapter that has a bit of other information with the K corrections for it here, and I'll send that to you later on.
thanks. And there are lots of compliments pouring in. If you can see the chat window,
Oh
we all
yes, yes.
understand you're like sitting up middle of the night for us, and that
Well, you're all welcome, and I do appreciate those nice compliments there. Thanks a lot for those.
Thanks a lot. It was lovely. Your lectures were very well taken and very informative. Thanks a lot.
You're welcome. I appreciate that. Good luck with your grading there, with
Yeah,
your test grading.
yeah.
so thanks a lot, and we'll keep in touch. Yeah,
Okay, you too.
yeah.
Good
Bye
night.
bye.
Good morning.